This video is sponsored by CuriosityStream. Get access to my streaming video service, Nebula, when you sign up for CuriosityStream using the link in the description. We often discuss terraforming Mars and other worlds, of giving them oceans and atmospheres, but for these worlds to keep them, we may need to give them magnetospheres as well. So a popular topic in science fiction, and on this show is terraforming of Mars. This comes in two forms: para-terraforming, which is the classic big domes with air and life inside, and terraforming the world entirely to have its own atmosphere and seas that can be naturally retained and support life. Now, you've probably heard theories that Mars used to have air and seas and lost them over time, and many culprits are suggested, but the two big ones are the low gravity on Mars and its lack of a magnetosphere. These two, plus some others, are not either-or cases. Indeed, Mars' low gravity and lack of magnetosphere are related issues, and both doubtless contributed to it losing an atmosphere if it used to have one, and more importantly, are problems for giving an atmosphere in the future and keeping it on there. Needless to say, our big focus for today is going to be on the magnetosphere component. But to explain why Mars needs one, or a substitute, we need to explain how atmospheres leak into space, or into the ground for that matter. Most rock is made of oxygen, for instance, and how a magnetosphere helps prevent that leakage. Into space anyway. Though a magnetosphere generated by a molten core probably helps with recycling the land, and oxygen sequestered into it, by having higher tectonic activity. We also need to emphasize that terraforming is a long process of centuries, if not millennia, but atmospheric leaking is a process over geological periods. Earth leaks air, about 30,000 tons a year, and everything with an atmosphere leaks air. 30,000 tons might sound like a lot, but our atmosphere is 150 billion times more massive than that. It also means that we need to bring in or generate all that air to some planet we're terraforming in just 1,000 years. That's 5 trillion tons a year, 150,000 times the rate Earth leaks at. So even leaving just a fraction of the original air importation infrastructure or generation infrastructure in place would allow you to keep up with that leakage rate from a planet, even if it was hundreds of times what Earth has for leakage. In that sort of context, when folks ask if Mars needs a magnetosphere to keep an atmosphere, the answer is no. No civilization able to put an atmosphere on a planet is going to think it's an impractical chore to keep up with the leakage caused by not having a magnetosphere. That is something we need to contemplate while we are contemplating our options for getting that magnetosphere or other leakage control options, because in discussion of the topics, there's an impression that they're dealing with a life and death immediate issue. It is not. This is an issue of slow loss over millions of years. So responses, or efforts like nuking their planetary core 1 billion times in some weird attempt to spin it up, are not likely to be considered preferable to continued importation or other loss prevention methods. As an example, Venus has an atmosphere much thicker than Earth's, and only a weak magnetosphere. Venus loses about 10 trillion hydrogen atoms a second, though that only amounts to about 500 tons of hydrogen a year. Earth loses about 200 times that and is further from the Sun, which is what magnetospheres principally protect us from. Of course, we have a lot more hydrogen than Venus does, and it probably used to have more. So what is the escape mechanism that a magnetosphere stops or hinders? First off, there are many ways that incoming radiation strip atmospheres off worlds, and many mechanisms for atmospheric escape beyond that. But the majority of Earth's loss is hydrogen that presumably start off as water vapor in the air. We leak helium and oxygen too, but at vastly smaller levels. This is because particles of gas are no different than spaceships. They can't escape Earth without reaching Earth's escape velocity, roughly 11 kilometers or 7 miles per second. A hydrogen atom is a single proton, whereas helium is 2 protons and 2 neutrons, and oxygen is 8 of each, 16 times heavier. It takes a lot less kick to knock hydrogen up to speed, and the velocity of particles randomly floating around our air is generally influenced by the local temperature and the mass of that particle, And particle might be a lone hydrogen atom, or it might be a molecule like water, which is 18 times heavier, or carbon dioxide, which is 44 times heavier. Hotter is faster, and lighter is faster, going with the square root of temperature and the inverse square root of mass. As an example, a carbon dioxide molecule and a lone hydrogen atom in the same temperature gas mix generally will have that hydrogen atom moving about 7 times faster, as the square root of 44 is 6.6, rounding up to 7, and an oxygen molecule and nitrogen molecule, the main components of our atmosphere, mass in at 32 and 28 times heavier than hydrogen, and will move 5.7 and 5.3 times slower. If you're curious, that speed is about 500 meters per second for oxygen and nitrogen molecules at about room temperature, and a lone hydrogen atom would be more like 2500 meters per second. Now this is not the actual speed of each particle, it's what we call the root mean square speed, and it's more like the peak of a bell curve of speeds, with some faster and some slower, and a far smaller outlier of those going much faster or slower. Generally, the bigger the particle and the thicker the gas, the tighter that bell curve will be, because it takes so much more to push a big particle to high speed, and as soon as it gets faster, it is more likely to run into slower peers and collide, especially in a thick gas. So what's principally going on is that gas escape is happening from Earth's upper atmosphere, the ionosphere, which gets the name from all the charged particles or ions that have risen up to the thin top of the atmosphere, because somebody has to, and it's generally those lighter and kicked particles. That kick is often coming from ultraviolet light, which a magnetosphere does nothing to stop. Now, ultraviolet impacts escape mostly and they can break molecular bonds, resulting in multiple smaller particles, but ultraviolet photons are also powerful, as much as 12 eV or electron volts. Normal visual light is about 2 to 3, and a hydrogen atom hit by one gains a decent amount of speed. And up there in the thin ionosphere, especially its highest layers, things are so spread out that particles are able to move long distances and times without running into each other, so they can keep getting hit by photons or extraterrestrial particles and build up speed, and can potentially get up to orbital speed, which is well below escape velocity still, but means they're staying up there until they hit something else, and that's very likely to either be particles moving similarly fast or more photons that can add speed. Now this mechanism, and the one that accounts for most of Earth's loss, is called the Jeans escape mechanism, and we do have a magnetosphere, a very strong one. Interestingly, you get a higher amount of loss close to the equator as Earth's spin adds to particle velocity in the same way it does for spaceships, and of course there's more light incident on particles there too, and also solar wind. Now what the solar wind does is far worse, as solar wind is principally composed of ultra-hot ionized hydrogen particles escaping off the sun's surface at hundreds of kilometers per second, meaning when one of those particles hits a hydrogen particle from Earth, those collisions will generally result in both particles still having more velocity than they need to escape from Earth. Indeed, multiple collisions could occur before that stops being the case. And more often than not, one of them is emerging with a vector that doesn't bring it ramming back into the planet, which matters as it's about direction too. A fast rocket aimed at Earth is not escaping from it, no matter how fast, though some of its vaporized atoms might after the collision. After all is said and done, the particles that hit Earth from the sun tend to rip atoms off more often than they stick around, and of course big coronal mass ejections can smash us with vastly more. Now remember that Venus gets hit by way more of this than we do, and has no magnetosphere to compare to ours, and still leaks little, and that's because it just doesn't have much hydrogen to leak. I want to underscore that because it's not really atmosphere leaking away, it's hydrogen. Oxygen and nitrogen are vastly more resistant to escape, especially in molecular format, but a solar wind hydrogen particle hitting a 16 times more massive oxygen atom just isn't getting the same velocity kick. So in many ways, we're not talking about breathing gas disappearing or the nitrogen that plants need. We are talking about the slow loss of water from a planet. Our oceans mass around 1,000 times more than our atmosphere does, so it is going to erode away a lot slower. Though as our sun heats up and ages, the stripping rate will increase enormously. Now, what does the magnetosphere do? Well, firstly, it tends to deflect particles away. Ions moving through a magnetic field are pulled toward or pushed away from it, Note that the solar wind is protons, electrons, and some heavier particles, and they do sometimes capture each other and thus stop being electrically charged, thus mostly ignoring magnetic fields and magnetospheres, but still moving fast. So again, magnetospheres alone do not completely protect worlds, and of course magnets do not directly affect photons, be they visible light or higher energy ultraviolet, X-ray, or gamma ray photons. Charged particles trying to escape Earth can also be knocked back or deflected, keeping them from escaping. Interestingly, we have another escape mechanism called charge exchange escape, which is where a high-speed ion captures an electron off a passing slow neutral particle, turning them into a fast neutral particle and a slow charged one, and this fast neutral can now pass through the magnetosphere with ease. While natural magnetic fields by spheres are our default perspective, it is worth noting that we can also achieve deflection between two big charged plates, and the protons or ionized hydrogen would head one way and the electrons another. Not our main focus for today, but civilizations might be aiming to harvest these incoming particles rather than just shield from them, and as harvesting still achieves the protective effect, these routes might be considered the waste not, want not profitable method. We will be getting to making artificial magnetospheres shortly, and we need to be mindful that some big sphere designed solely for deflection might be considered a very inferior approach. It's also not really a sphere, and indeed Earth's dayside magnetic field is significantly compressed toward Earth from the constant barrage of charged particles off the Sun. They can also escape via polar wind, as near the poles of a magnetosphere the magnetic field lines are open, allowing a pathway for ions to escape into space. Incidentally, not everything is going to be coming from our Sun, although the term cosmic rays is quite the misnomer these days. We used to think these were principally electromagnetic radiation back before we could actually get probes up into high orbits. It's mostly high-speed particles though, not photons. About 1% are electrons, then 90% protons, and about 9% alpha particles, helium atoms minus their electrons. About 1% are heavier ions, HZE ions as they are called, and the nuclei component of galactic cosmic rays or GCRs. Most heavier ions still come from the Sun, but we get GCRs from outside the solar system, and they're usually moving at near light speed and are thought to be principally coming from supernovae shockwaves. These are ruinous, because while the hundreds of kilometers per second that solar wind moves at seems fast, light speed is 300,000 kilometers per second, 1,000 times as fast, meaning they've got around 1,000,000 times the kinetic energy of the solar wind, particle for particle. Rare but vicious, and why we tend to discuss nearby supernovae as dangerous to our atmospheres. The explosion itself, while huge, is still so far away from even the nearest neighboring stars that the popular image of them tearing a planet apart is ridiculous, but they could still be a real danger to an exoplanet by damaging its atmosphere. With that in mind, we will discuss some types of solar shields that are placed between the planet and star, and thus don't help against extrasolar cosmic rays. So when building our artificial shielding, we might be contemplating multiple approaches simultaneously, which also means multiple layers of protection against failure and sabotage. This also brings up recovery as another layer of protection, because most of these escape particles have a charge in a general direction off the planet. The big plasma sheets or trail that all worlds with atmospheres generally have behind them as a result of their sun. And much as we might put a magnetic deflector at the planet's L1 point with its sun, we might put a catch bag at its L2 to absorb it all. And in reality, planets we terraform and colonize are likely to have huge orbital infrastructures, and many will have their own small magnetic shields, so it might be a minor cottage industry for them to serve as buffer, deflectors, or absorbers of solar wind and escaping atmosphere. Now, L1 and L2 are short for Lagrange 1 and Lagrange 2. The first and second of 5 Lagrange points every planet has with its star, and every moon has with its planet. These are spots that orbit with the planet or moon where you can leave hardware and expect to stay stationary with minimal help. They are only metastable, so they do have to do a fair amount of station keeping anyway, but it's way less, and for instance, one of the ways you can potentially do station keeping is by surfing on solar wind and radiation pressure. What's neat about the L1 and L2 is that L1 is directly between a planet and its star, and L2 is directly behind, and the same for planet-moon Lagrange points. Earth's L1 with the Sun is about 1.5 million kilometers from Earth toward the Sun, about 4 times the distance from us that the Moon is, and about 1% of the distance to the Sun. The L2 is the same distance behind us. Now this is a great place to put a giant magnet that would deflect particles away from a planet, though I will take a moment to note that it is getting shoved on by that solar wind, not just dueling gravity from Earth, the Sun, and a disruptive moon, or in this case Mars and the Sun, as Mars moons are trivial. As a result, this giant magnet wouldn't actually be at the L1 point. Similar applies to big thin shades or mirrors we might use for warming or cooling a planet. The force of solar wind and sunlight is just too enormous in their case, being thin and sail-like, to ignore, and thus they all become examples of lagites or lagging satellites, a concept we first detailed on our episode Chicada thrusters back in 2016. And a trick we can use with relatively big and light objects, as opposed to heavy dense rocks like planets and asteroids, is to create very atypical orbital patterns, as an extension of the static satellite or statite first proposed by Robert Ford in 1993, and also a bit like the halo orbit options for solar sails from Colin McInnes. As we discuss sticking things at L1, these concepts alter it from a single, relatively small point to a vast region of space we can put a lot of objects in, including solar mirrors off to the side that are quartering the sunlight to bounce some to their ward and use the rest to remain relatively stationary. I think one objection folks have to an artificial magnetospheres in orbit or an L1 is that they limit the use of that space for other options. This gets around that. Now you're probably thinking it must take an insane amount of energy to replicate a planet's magnetic field, and of course a giant space array of solar panels at the L1 can help with that, but it's actually not that much energy. See, the thing is, a big molten globe of spinning metal in a planet generating a magnetic field may be how they are naturally generated, but this is a horribly inefficient way to make one. That's why our own electromagnets here on Earth do not use that approach. This is actually a case where a big piece of planetary engineering is pretty cheap. See, solar wind being deflected by a planet when it's moving so fast requires a lot of deflection as it's already pretty close. If you're starting 1 million kilometers out, Mars' L1 point is 1.018 million kilometers toward the Sun, then a smaller deflection of a particle in terms of angle will knock it further to the side before it gets to Mars. We can achieve a parallel level of deflection for Mars by knocking incoming particles about 3,000 kilometers off course, 1 million kilometers away, or by knocking incoming ionized particles just 0.2 degrees off course by running an electromagnet out there that's much less powerful than we would expect, and I've seen calculations as low as what we would get out of a fairly large nuclear power plant or hydroelectric dam, or a few square kilometers of solar panels. The amount of energy needed to be stored in this electromagnet is in the range of 10 to the 17 joules for Mars, and while that's not a trivial figure, the equivalent of thousands of Hiroshima-strength A-bombs, it is still tiny compared to what an industrial nation uses for electricity in a year, and is comparable to the total sunlight hitting Earth or Venus or Mars in any given second, or maybe a few seconds for cold and small Mars. Now that energy in the magnetic field needs replenishing, though the exact rate is hard to say. A magnetic field does no work on objects, it just bends trajectories, but everything leaks, whether it's the atmosphere of a planet or the magnetic field guarding it. But replenishment times are months, not minutes here, as a very loose approximation. This is probably the cheapest and easiest approach, and my general thinking is that something along these lines is going to be standard for any planet, just because a settled world with all its orbital infrastructure has a lot of cause to want to deflect that solar wind around them. Planets with magnetospheres look like giant torches moving through space in terms of all the ionized gas whipping around them and leaving a wake of plasma. They are dangerous places too. The Van Allen radiation belts around Earth include a very large amount of orbital territory we will want to use one day, and while we can thickly armor and shield our infrastructure up there, the whole area is saturated with ionized particles held around the planet by our magnetosphere, and a good reminder that a magnetosphere does not make everything safer in every regard. Think of the inner and outer Van Allen radiation belts as constant sandstorms of ultra-fast charged particles and ionizing radiation. So a big shield at L1 is handy even for Earth because it would do a lot to bring those belts down a couple notches and further protect us from big solar storms and coronal mass ejections. It's making it safer and easier to operate in orbit, extending the lifetime of orbital objects, cutting down the shielding they need, and also cutting down on noise. There's a lot of radiation in the radio range for those belts too, and from all that solar wind, heck, you can hear the planet Jupiter on 14 to 38 MHz with a decent amateur radio set. This is the range of high-frequency radio waves, often called skywave, because it will bounce back down off the ionosphere and those ionized particles. For that matter, we often contemplate engaging in starlifting on our sun, magnetically pulling matter off the sun as a way of mining it for valuable metals beyond what the rest of the solar system combined possesses, and that's likely to kick up a lot of solar wind. And a highly active interplanetary civilization running itself on ion drives, fusion torches, or nuclear rockets is one that might see a lot of extra particles kicking around as exhaust too. And many of these technologies work not just for Mars and Earth, but also colonies on various asteroids, dwarf planets, and moons. So needless to say, there are some good reasons to want to set up an L1 magnetic deflector, especially given that it is not a high power draw even by modern standards, let alone in comparison with some of the titanic energies needed for terraforming, or available to any civilization contemplating that instead of para-terraforming options like domes. That said, this option is not exclusive nor complete. There is plenty of reason, for instance, to still want to live in a dome, even if your planet has an atmosphere, as one that you can modify the opacity of or open at will offers some excellent climate control options and also provides an extra layer of protection. We always want layers and contingencies after all. I'm guessing some of you thought, when I mentioned shielding Earth to decrease radiation in orbital space, that if we built in that decreased radiation zone, then those facilities would all be subject to danger if accidental sabotage, or threat of it, turned off that L1 deflector. Now first, we can't have multiple in place that are end backups, and second, we're talking about a rise in radiation levels, not an explosion that instantly kills folks. The inner Van Allen belt is more radiation saturated than the outer, and we guess you could do 71 days minimally shielded in that before hitting lethal radiation doses. Even assuming you don't have better technology by then for treating radiation illness, that's a long time to be fixing your magnetic shields or bolting extra armor onto your facility, and we would still expect them to have thicker hides than modern stations and ships anyway. Nonetheless, it is always good to have more backups. That can and probably does include a magnetic grid around that planet, as opposed to at distant L1 alone. We often talk about orbital rings on the show, huge hollow rings that stand stationary or slow rotating with their planet below, while inside tons of charged matter orbit around the world at super-orbital velocity while magnetically contained. This same core bit of space infrastructural technology also allows giant space towers or huge elliptical launch loops stretching from a planet's surface up to high orbits, and it also allows us to generate huge magnetic fields around a planet and its orbital space to deflect solar wind away by running a lot of charged particles, or electricity, around in a contained loop, a torus or even a big wide belt of a solenoid. You may opt for permanent magnets or electromagnets. I would bet on the latter, though the problem with an electromagnet is that it stops making a magnetic field when you cut off the power. However, solar power works really well in space, where there's no cloudy days, especially at Lagrange points, and higher orbits, where nighttime is short or non-existent, as they spend less time in the planet's shadow or night. So a big donut is possible. Indeed, we've even discussed megastructural orbital habitats that are rotating rings around a planet that people live upside down on, and such a place might also serve as the planet's magnetic shield. Or we could have arrays of individual satellites networked to make a shield, and this also helps protect against GRCs from extrasolar sources. There have been a few papers on this topic and more or less formal work on the science forums down the years that we discussed before, but for those looking for a deeper dive into physics and calculations, there was an excellent paper by R.A. Bamford et al., How to Create an Artificial Magnetosphere for Mars, that came out some months back that I thought did an excellent job cataloging some of the Martian magnetosphere options and running the numbers, and I'll link the PDF in the episode description. One thing I did appreciate them going into was the Martian core restart, and the case we'll discuss in a moment of magnetically spinning it up. Now, typically people envision this as some massive nuking process where we bore a hole down to the core to dump billions of H-bombs designed to both heat up and spin the core. This would kill everyone on the surface and is a bad idea. We have discussed the idea of setting up super tall towers up to orbital heights, with big mirrors on them, to turn a planet into a pinwheel you could hit with lasers to spin the planet up faster or slower as a way of altering the day length, and you could also run those towers deep into the core to dump heat energy into the world too. I want to emphasize that both of these ideas are very high energy options. Figure on it requiring at least 10 to the 30 joules of energy, more than 1 trillion times the energy in that magnetic shield we mentioned earlier, and leaking out at a rate of several trillion watts too, a lot more than that shield took to keep running. We are talking about superheating around 1 billion trillion tons of rock and metal here, and doing this at any rate of speed means totally cracking, tearing, and warping the crust at an epic scale, as in way off the Richter scale. But it could be done slower, as suggested with those big pinwheel towers. Just as spinning a ball of molten metal can generate a magnetic field, it is also subject to magnetic fields, and we do think Mars has a molten core, albeit a small one, so we can build a huge magnet around it, encapsulating Mars in a protective magnetic field powered by huge solar power, and begin shoving on that core to spin it up. The extra drag and force of that spinning effort will turn it into heat, melting and expanding that core, and at the same time you could have good thermal conductors drilled deep into a world that you pumped heat down to help with that too. This is a slow process, directing a full terawatt of power into a world this way and ignoring its own heat leakage that would still take 10 trillion seconds or 317,000 years to hit that 10 to 30 joules minimum energy I suggested a moment ago as needed to heat that core up. Still, that's doable, and you could even raise that up a bit, especially given excess heat would help to terraform cold Mars. Done right, you could probably spike the core with some thick rods carrying sunlight-generated heat to the core to keep it from cooling too, and maybe even use all that as thermal piles to run buried electromagnets. A magnet need not be in orbit or at L1, it could be a huge underground cable wrapped around the equator too. So, for the purists out there who want a Mars that might one day have its own natural magnetic field able to protect it without technology or maintenance, yes, this really is an option, and one that you could probably pursue in tandem with all the other easy technological approaches we mentioned today. I think it's probably overkill and unnecessary, but then I'm not planning to live there. Future Martians might feel different and more ambitious. After all, if you shipped in and built your oceans and sky, then you probably do not feel the sky's the limit on your ambitions and undertakings. Mars seems ever closer to the day where we will first land humans there, and in between that moment and vast engineering projects for the Red Planet like we discussed today, there will be those first colonists working on becoming Martian, and there's a great 3-episode series contemplating life there, Becoming Martian, over on Curiosity Stream that I highly recommend, and it's just one of many shows looking at Mars over on Curiosity Stream. Now, we also mentioned Jupiter's magnetosphere today, which is enormously powerful and results in a vast amount of radiation hitting those 4 giant moons around Jupiter, Io, Callisto, Europa, and Ganymede, which we would like to colonize too. I thought we would take a little time to discuss handling that in the context of creating and manipulating magnetospheres, so we also have an extended edition of today's episode over on Nebula, where we'll be discussing how we can make the Jovian moons and orbital space safe for human habitation by manipulating Jupiter's magnetosphere. Nebula is our streaming service created to give YouTube creators more flexibility and not be at the whim of YouTube's algorithms for our content, or any other platform. It is the largest creator-owned streaming service in existence, and all of SFIA's content is up there, ad and sponsor free, and released a couple days early. We also release an extended edition or two every month, and have some exclusive content like our Coexistence with Aliens series. It's a great way to help support some of your favorite channels while getting ad-free content. Now, you can subscribe to Nebula all by itself, but we've also partnered up with CuriosityStream, the home of thousands of great educational videos like Become Emotion, to offer Nebula for free as a bonus if you sign up for CuriosityStream using a link in our episode's description. That lets you see the amazing content on CuriosityStream and Nebula for less than $15 a year. Just use the link in the episode's description. So we're done for today, but not for the week, as we have our Sci-Fi Sunday episode, Lost Space Colonies, and what would happen on them coming up this Sunday. Then we'll be launching a new miniseries looking at finding and exploring distant worlds, surveying for habitable interstellar star systems, on Thursday, May 19th. Then we'll close out the month with a look at dark sky stations, stratospheric satellites, and ultra-low orbital infrastructure. As a reminder, our normal monthly livestream will instead be held at the International Space Development Conference on Sunday, May 29th at 4 p.m. Eastern, where I will be giving a live talk on megastructures. Then we'll jump into June and start the month by asking what ancestral simulations are and if we are living inside one. Now, if you want alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, please hit the like button and share it with others and leave a comment below. You can also join the conversation on any of our social media forums, find our audio-only versions of the show, or donate to help support future episodes. And all of those options and more are listed in links in the episode description. Until next time, thanks for watching and have a great week.